You know, it's a situation you've probably found yourself in. You're trying to recall this highly specific conversation you had,
Oh, absolutely.
or maybe there's a technical fact you stated out loud, and it's just buried somewhere in hours and hours of your own audio recording.
Right, in a mountain of digital files.
Exactly. You have this massive archive of your own voice, your own thoughts, but you're trying to find that exact 10-second window where you talked about a highly specific concept. And the traditional workflow for this is just universally terrible.
It really is. It's the cassette tape paradigm.
Yeah, you're just scrubbing through raw audio files, staring at waveforms, guessing the timestamp, getting frustrated, and then probably just giving up.
Which makes sense,
Yeah.
because chronological format is really the enemy of rapid retrieval. You're fast-forwarding and rewinding, just hoping to catch a momentary snippet.
But what we're looking at today fundamentally breaks that whole paradigm. We are jumping into our deep dive, the second part, actually, of a massive, ongoing technical journey.
And it's a fascinating one.
It really is. We have this incredible set of developer notes, system logs, and architectural diagrams following a developer named Vitaly. We're tracking his foray into LangChain, specifically a project he titled LangChain, Cautious Experiments in Vectorizing Podcast Timelines.
The mission here is incredibly ambitious, especially when you look at the constraints he placed on himself.
Right. So the setup is Vitaly set out to build a vector memory. He wanted a searchable, persistent, intelligent database of his own previously published podcast episodes from his YouTube channel, which is called Rag to Riches AI.
A great name, by the way.
Totally. So he's taking plain text subtitle files, those standard .srt files you get from video editors, and feeding them into a local ChromaDB database.
Yeah.
But before we get into the heavy software engineering, we really need to do a reality check on the hardware here.
We definitely do, because when most people hear about building an AI system to ingest thousands of lines of text and perform mathematical embeddings,
They're running a large language model to query it.
right, they immediately picture a massive corporate cloud environment, rented server racks, enterprise budgets.
But Vitaly is doing this entirely locally. This is not happening in the cloud. He is running this entire architecture on a consumer laptop.
Which is wild.
It's an AMD Ryzen AI9 HX370 CPU paired with 32 gigabytes of system RAM. And the real bottleneck, the crucial constraint, is his GPU. He's using an NVIDIA RTX 4060 laptop GPU.
Yeah, that card only has 8 gigabytes of VRAM and a 54-watt maximum power draw.
8 gigabytes.
Yeah.
And on top of that strict hardware limitation, he is utilizing the Llama 3.1 8 billion parameter model.
Okay, let's unpack this, because that is a brilliant but frankly terrifying constraint.
It's claustrophobic when you're talking about loading a generative language model and running an embedding pipeline simultaneously. 8 gigabytes of VRAM gives you almost zero margin for error.
You can't just throw sloppy code at a messy problem.
Yeah.
You have to be surgical. If you spike your memory usage by even a few hundred megabytes, boom, the whole system crashes with an out-of-memory error. Exactly. But operating under extreme constraints forces you to make the invisible visible. It forces you to understand the architecture of your data pipeline at a microscopic level. The logs we have from Vitaly's terminal are basically a masterclass in local AI development.
We get to see him hit brick walls and engineer his way over them, and the very first brick wall he hits is the raw data problem. Because to build a memory, you first have to feed the AI the data, and raw data is super messy.
Oh, it's absolute structural clutter.
Right. If you open a standard .srt subtitle file in a text editor, it's not a nice, clean script of dialogue. The format usually dictates a sequence number, like a 1, sitting on its own line. Then below that, a rigid timecode, like 0.01.20 thousand, an arrow, and another timecode.
And then finally, beneath all that metadata, you get a few actual words of human dialogue.
So why is that a problem? Because for a semantic vector database, that rigid numerical structure is highly toxic.
Extremely toxic. If you feed those raw time codes into ChromaDB alongside the text, it completely pollutes the vector math.
Wait, let's dig into that why for a second. We talk about converting text to math, but visualize what the embedding model is actually doing when it hits a timestamp.
Okay, think about the core function of an embedding model. It takes a piece of text and maps it to a high-dimensional mathematical space. Concepts that are semantically similar get placed close together.
Right.
Now, if you leave all those sequence numbers and timestamps in the text, the AI gives mathematical weight to those digits. The model doesn't inherently know that 0.00.05 is a metadata tag to be ignored.
It just sees it as information.
Exactly. It treats it as a token. So if you ask the database a conceptual question about, say, local vector databases,
Mhm.
the database engine searches for mathematical proximity. If your subtitle chunk is polluted with numbers, the vector calculation gets skewed.
So the AI might heavily match your query to a random chunk just because the numbers align in some weird high-dimensional way instead of the actual concepts.
Precisely. The numbers become dense semantic noise that drowns out the actual meaning of the words.
So Vitally realized he had to sanitize the data before the embedding model ever touched it. He wrote a custom regex, a regular expression cleaner function in his Python script,
Which is essentially a highly specific string matching algorithm.
a digital vacuum cleaner. He told Python to sign any block of text that looks exactly like a timecode and just delete it. He ran this over his files, stripped out every sequence number, every timecode, until he had pure, unbroken dialogue.
And then he instituted a chunking strategy.
Yeah, he split this clean text into manageable blocks of 150 characters with a 30-character overlap.
That overlap is a fundamental pillar of Retrieval-Augmented Generation, or RE. A 150-character chunk is roughly a sentence or two. It's a tight unit. But human speech doesn't always break cleanly into 150-character boxes.
You risk cutting a thought right in half.
Exactly. So the 30-character overlap acts as a bridge. It ensures the end of one chunk is repeated at the beginning of the next, maintaining the flow of ideas.
But wait, looking at this from a pure utility standpoint, we hit a glaring paradox. The whole goal was for Vitali to find specific moments in his podcast history. If his reject script deleted all the timestamps, haven't we just ruined the ability to find a specific moment in the video?
It does seem that way, doesn't it?
It's like ripping the page numbers out of a book's index so the paragraphs look cleaner. How is he ever going to know when he said something?
What's fascinating here is how LangChain handles this exact duality.
Yeah.
You need the text pristine for the mathematical embedding, but you need the rigid timestamps for human utility. LangChain solves this with document metadata.
Okay, break that down for us.
In the LangChain ecosystem, every piece of information you pass in is wrapped in a Python document object. And that object is split into two distinct parts.
Yeah.
You have the page content, which is the raw, clean text the embedding model actually reads.
And the second part?
The metadata. It's a hidden Python dictionary natively attached to that specific chunk of text.
Oh, wow. So it's an invisible registry that rides alongside the text?
Exactly. So Vitali updated his Python script. Instead of throwing the regex matches in the trash, he captured them. He extracted the start and end times for every chunk and injected them into that hidden metadata dictionary.
So the embedding model doing the complex math only ever sees the pure sentence, but as that sentence is pushed into ChromaDB, it carries this hidden backpack containing the exact minute, second, and millisecond.
The database architecture indexes both simultaneously. It builds the mathematical graph of the vectors and a lookup table for the metadata. When you query it later, you can instruct your Python script to unpack that hidden backpack and print the timestamps right next to the answer.
That is an elegant solution. The mathematical purity is untainted, but the tracking precision is absolute. Okay, so armed with this single file solution, Vitali needs to process his entire backlog of episodes automatically.
Right, doing it file by file would be excruciating.
So he builds an automated batch ingestion script, creatively named vectorizer.py. It automatically searches the local folder for .srt files, extracts the episode title from the very first line of the file, cleans the text, injects the metadata, and pushes it to ChromaDB.
The shift to automated batching is where local programming truly unlocks its value. But there's something about the hardware utilization during this phase that's really important to note.
Yes, I was surprised by this. Vitali does not need to have his massive LLM Llama 3.1 running to do this ingestion.
Understanding resource allocation is critical when you're trapped within a 54-watt power limit. A model like Llama 3.18b consumes gigabytes of VRAM just to sit idle.
So what's actually doing the work?
The text-to-vector embedding relies on a tiny local Hugging Face model called All-Middle-LM L6v2. It runs independently via PyTorch on the RTX 4060 GPU.
It's a dedicated tool.
Exactly. It converts text into math without needing the heavy Llama server active. It only takes up about 400 megabytes of VRAM. It executes the mathematical conversions incredibly fast, while the massive Llama model stays completely dormant on the hard drive.
It's a beautiful separation of hardware concerns. But before he runs the batch ingestion, he brings up a major concern. He already has a vector database storing his personal secrets and router passwords on this machine. Should he mix his YouTube podcast transcripts into the exact same database?
Any traditional SQL database engineer would panic at that idea. They'd say, absolutely not, spin up a new isolated instance.
Right, dropping my Wi-Fi password into a bucket of public AI podcast transcripts sounds like a disaster. I'd be terrified the AI would hallucinate and spit out my network security keys.
It sounds chaotic, but he absolutely should mix them. It requires a paradigm shift. We have to look at the physics of vector space.
The physics of vector space, I love this concept.
Stop thinking of ChromaDB as a traditional filing cabinet. Visualize a vast, high-dimensional universe. The all-middle LM model outputs a 384-dimensional vector. Every chunk of text is assigned a mathematical coordinate across 384 axes based on semantic meaning.
It's like plotting a point on a graph, but with hundreds of directions representing concepts.
Yes. Now, analyze the vocabulary of a router password versus a podcast about AI. Random characters and IP addresses versus Python scripts and R architecture. Because the vocabulary is so vastly different, they map to entirely separate neighborhoods in this high-dimensional space.
They live in the same database universe, but mathematically, they're light years apart.
They will never collide. If you ask about your router, the system measures the vector of your question and searches for closest neighbors. It's mathematically impossible for it to jump across the universe and pull a quote about Python because they share almost zero vector similarity.
It's a unified local intelligence engine.
Exactly. It naturally compartmentalizes knowledge purely through the math of human language.
So Villali embraces the single-brain approach. He runs his vectorizer.py script. The logs show he successfully processes and uploads 7,691 chunks of text in a flash. He has successfully built the memory.
But ingestion is never the true test. Retrieval is.
Right. And this brings us to the spectacular double failure. The database is loaded. Villali fires up his terminal. This time, Llama 3.1 is awake. He types, "What were the main topics discussed in episode 3?
The perfect control question.
What happens next is comedy gold. The database debug mode shows Chroma found 0 matching snippets.
Nothing.
But Llama 3.1 doesn't say, "I don't know." Instead, it confidently responds with a detailed, completely fake outline stating, Episode 3 was about self-care, mindfulness, and the benefits of meditation.
And when he tries again, it hallucinates an outline about an exclusive interview with a NASA astrophysicist discussing Mars exploration.
It's a spectacular double failure. Let's break this down, starting with failure 1, the database miss. Why did Chroma find 0 snippets?
It's the Python logic of the ingestion script versus the retrieval script. His ingestion tool generated a clean ID from the file title. It took podcast episode #3, local AI development, swapped spaces for underscores, and generated the ID podcast episode 3 local A development.
But his terminal script searched strictly for podcast episode 3.
Exactly. A strict exact match lookup. In strict Boolean logic, close doesn't count. No exact match meant no data retrieved.
Okay, so the database gave Llama an empty folder. That brings us to failure 2, the LLM lie. Why did Llama make up an elaborate lie about NASA?
This exposes the dangerous power of the system prompt. Vitaly had updated the prompt to command Llama to act as a friendly conversational companion.
Oh, no.
And in doing so, he removed the strict constraint, forcing it to state, "I don't know," when the context window was empty.
It became a people pleaser.
Structurally, yes. It saw a blank context window, but the prompt commanded it to be helpful. It saw the user's explicit request for podcast topics, so it fell back on its foundational internet training weights and hallucinated a plausible, fictional podcast outline based on statistics.
So Vitaly is staring at this hallucinated NASA outline, and he realizes his lookup is broken. He goes into diagnostic mode. He tries to fix the strict lookup by using a partial match filter, Chroma's contains operator, to look for anything containing episode 3.
A logical pivot.
He runs it, and it still fails. 0 snippets. This time, Llama hallucinates baking recipes.
This is where you have to stop trusting your assumptions and look at the raw metal.
Yes. Vitaly writes a diagnostic script, checkgb.py, to print the raw, unfiltered contents of the database directly from the SSD.
Bypassing all the filters. And what did he find?
The shocking output. It prints total vectors, 7,696. The data is there, but then it prints raw metadata dict. None.
A black hole.
The data was there, but the metadata was missing entirely. Why?
Because of how data serialization is handled between LangChain and Chroma's underlying SQLite database. Vitaly used an older method, chroma from documents, passing composite objects.
Which seems straightforward.
It does. But in certain versions, if the SQLite table is initialized without explicit column schemas for the metadata keys, the ingestion engine doesn't know how to map the dictionary to the SQL table.
So the system routes the text perfectly to the vector engine, but drops the metadata payload on the floor.
It fails silently. And if the database has literally no record of an episode read, filtering by it using two canes will return nothing.
So how did he fix it?
He had to physically delete the entire database folder, wipe the 7,600 vectors, and start from scratch. He updated the script to explicitly separate the text and metadata into two distinct flat Python lists using a method called chroma.fromTexts.
So he forces Chroma to bind them natively on the disk.
Exactly, row by row.
Okay, so the database is rebuilt, the metadata is intact. Vitally asks for episode 7, Chroma finds nothing. He asks for episode 7 with an underscore. Chroma finds the exact true snippets. Why?
This is the bizarre interaction between Python's regular expressions and Chroma's internal tokenizer.
It's madness.
It really is. Chroma indexes metadata strings based on strict internal tokenization rules. It uses punctuation, like underscores, as word boundaries. It chopped the stored ID into individual tokens, podcast, episode 7, etc.
But the Python regex tried to force a literal connected string search.
Right. The contains operator isn't a wildcard search like in traditional SQL. It looks for exact token matches.
Episode 7 with a space broke the string logic expected by the database ID.
One single space breaks the multi-gigabyte intelligence engine. So Vitali makes the ultimate architectural shift. He stops trying to use brittle metadata string filters.
He embraces semantic multi-filtering.
Instead of filtering the ID, he injects the episode number directly into the main semantic text search query, like episode 7 transcription text. What were the main topics?
If we connect this to the bigger picture, this is brilliant because it lets the vector embedding engine do what it's best at.
Yes.
It searches the entire 7,696 record index semantically, bypassing broken string filters entirely. It instantly pulls the most relevant blocks from the high-dimensional space. And it worked flawlessly. The AI memory core is finally functioning. Now, with the system working, the source document features a schematic diagram detailing the flow of data,
which serves as a literal blueprint for agentic AI chains.
Let's walk you through this flow. Step 1, CPU and RAM. The AMD Ryzen handles the Python routing, regex matching, and heavy indexing math.
Step 2, GPU, Part 1. The RTX 4060's tensor cores handle the ultra-fast text-to-vector mathematical embeddings, taking only about 400 megabytes of VRAM.
Step 3, SSD storage. Chroma reads the index binary straight from the local disk, saving active memory.
And finally, Step 4, GPU, Part 2. The Llama 3.18b engine uses the GPU's 8 gigabytes of VRAM to act as the ultimate filter, reading the raw context block, dropping irrelevant fragments, and generating the final streaming tokens.
Resource allocation is perfectly balanced.
It visually confirms the core principles of using vector databases within agentic AI chains. You don't need a supercomputer.
But as with all real-world engineering, there are lingering operational questions. The system is fast, but Vitali faces the vector soup danger. What happens if he leaves his old .srt files in the folder and runs the ingestion script again?
Oh, leaving files causes catastrophic database duplication. Chroma doesn't automatically deduplicate,
So you'd have multiple copies of the same episode occupying the exact same coordinate?
which ruins search performance and bloats the disk. The professional solution is an inbound archive architecture.
Vitali uses Python's shutil library to automatically move files to an archive folder the moment they are successfully vectorized.
He keeps the active ingestion zone permanently clean.
Then there's the list all episodes illusion. Vitali tries one last test. Show me all episodes headers. He expects a clean list of every episode. The AI only lists 2 random episodes out of dozens.
This is a masterclass on databases. Vitali was treating his vector database like a traditional SQL database.
What's the fundamental difference?
A traditional SQL database can scan a table from top to bottom and return a complete list, but a NoSQL semantic vector database does semantic math. It cannot scan a table.
It pulled the 3 chunks mathematically closest to the word list, and Llama simply read what was in those 3 chunks.
Exactly. To get a real list, you must implement an override fix. You bypass the LLM entirely and tell Python to query the raw metadata keys directly from the SSD using a command called vectorstore.get.
So you use semantic search for concepts and direct disk queries for structural lists. Okay, I want to wrap up with Vitali's final victory test. He searches for a highly specific phrase about emojis consuming tokens.
The ultimate stress test.
The system flawlessly pulled the exact quote from episode 2, cross-referenced a quote about exclamation marks from episode 7, and the LLM synthesized it perfectly.
This deep dive proves something profoundly important. You don't need a massive enterprise cloud budget to build a highly optimized, memory-persistent AI. You can build a world-class ARG or workspace entirely locally, privately, on consumer laptop hardware if you understand how to align the data flow.
It's incredible. And we would be incredibly grateful if you would subscribe to the Rag to Riches AI channel on YouTube, where this podcast is published. And please like this and other videos on the channel to support Vitaly's ongoing LangChain experiments.
It's entirely through sharing these conscious experiments that the community learns.
Absolutely. So I want to leave you with a provocative thought. Think about your own digital life. What messy, unsearchable archives of your own journals, meeting notes, project logs could you transform into a private, instantly searchable intelligence engine?
You have the hardware, and now you understand the blueprints.
How could you apply this architecture to your own data? Until next time, keep diving deep.